Hello and welcome to Lecture 2 of the Forces unit of Phys 1101. And in this lecture we're going to look at some of the common properties that all forces share, and then we're going to just list a whole lot of the forces that we will be dealing with commonly and look at some of their individual properties. And we'll sum up by just looking at how you identify what forces might be acting on an object. All forces come about because physical objects are interacting with each other. So take this shot put thrower, for example. With his hand, he pushes on the shot, or the ball. The ball pushes back on his hand. Similarly, if I lean on the wall, I push on the wall. There's a force that my hand exerts on the wall. But by the same token, there's a force that the wall exerts back on my hand. That's the force I feel. I can't feel the force that I exert on the wall. I would have to be the wall to feel that. Right now, if you pick up a book, you're going to lift it by pushing up on it with your hand. You will feel a force that the book exerts back down on your hand. We're going to see a lot more about this later when we study Newton's third law, because this is what Newton's third law is all about. But for now, I want you to be aware of it, because when you're thinking about a force acting on some object, it's easy to get confused and accidentally think instead about the force that that object is exerting back on some other object. We have a bit of terminology we use to talk about this. We say that every force is exerted by one physical object, and we call that the agent. So if my hand pushes on the wall, then my hand is the agent of the force. It's the thing that's doing the pushing. Every force is also exerted on some other physical object, and we can call that the target of the force. And I'll just warn you, that's my terminology. That's not normal physics terminology. So again, if my hand pushes on the wall, then the wall is the target of the force. This force is acting on the wall. And similarly, if we think again about the force that the wall exerts back on my hand, now the wall is the agent of that force, and my hand is the target. I'm going to make a really big deal of this, especially thinking about agents. I find a lot of students have problems that they have trouble identifying what forces ought to act on an object, and they'll often invent forces that don't exist. But if they focus on agents, if they focus on what objects can exert forces on the thing they're trying to think about, then they can usually avoid most of those problems. Being aware of the language we use can be helpful. There are a lot of cues that you can get from the way forces are described. If we say Bender exerts a force on the steel beam, Bender is the one exerting the force. He's the agent. The force is on the steel beam is the target. Similarly, if we say Stuart pushes upward on the banana, Stuart is pushing. He's the agent. The force is acting on the banana. It's the target. But we could turn this around and say there's a force on the banana due to Stuart. So now the force is on the banana. It's the target. Stuart is responsible for it. He's the agent. So if you want to push a chair across the floor, you would use a horizontal force. If you want to lift a chair, you'd use an upward force. So forces have direction, and the direction matters. It affects what the effect of a force will be. On the other hand, if you get frustrated with your computer and decide that you're going to throw your chair, then that's going to take a stronger force than it would take to lift it. So forces also have magnitude. We call the magnitude of a force its strength often. Well, so forces have both magnitude and direction. So that just tells us that forces are vectors. So remembering that forces are always between two objects that are interacting, one more thing we have to think about is whether they require contact between the two objects. So for example, when you lift a chair, you have to touch it, unless you're a Jedi, of course, unlike me. So the force that you exert on the chair is one example of a contact force, but not all forces are contact forces. There are also long-range forces. Gravity is a long-range force, and it's really the only one we'll deal with in this course, but electrical forces and magnetic forces are also long-range. All we mean is that there's no contact required between the agent and the target for the force to act if it's a long-range force. We need to take some time to just catalog all the sorts of forces that we'll be encountering. And this is going to seem like a lot to remember, but don't think of it as things you need to memorize. If you connect these ideas with your own experience, you'll realize that much of this is just common sense. You just may have to interpret your common sense a little differently from how you have in the past. So the first force we need to think about is weight, and it's also called the gravitational force. This is the only long-range force we'll really deal with in this course. We'll look at electricity and magnetism in Phys 1201. And the gravitational force is exerted by every mass on every other mass. So you see this diagram where I've said there's a force that the sun exerts on the Earth, a force that the Earth exerts on the sun, and so on. But for our purposes, we're usually concerned with things that are on the Earth. And for objects on the surface of the Earth or flying in the Earth's atmosphere, the only gravitational force we really need to worry about is the gravitational force acting on them due to the Earth. And notice that's telling us the agent. So unless you're thinking about something that is not on Earth, the agent of the gravitational force, the weight, is the Earth. And in that case also, it always acts down. And we're going to represent weight by a W, but you'll see in many sources it gets represented by an F sub G. Next, we're going to look at the spring force, and we're looking at it next because it's helpful for understanding how some other forces work. It's a contact force, and as its name implies, it's exerted by springs, but it's also exerted by anything else which can be thought of as springing back to its original shape, like this fishing rod. It always acts back towards equilibrium. What do I mean by that? I mean, if you take a spring and you compress it, then the force that the spring exerts back on your hand is back towards the uncompressed length of the spring. And similarly, if you take a spring and you stretch it, it pulls on your finger back towards its unstretched length. And finally, the amount of force that a spring exerts depends on how far you stretch it, or for something else like a fishing rod, by how much you've deformed it. So the next force we're going to look at is tension. It's another contact force, and it's exerted by ropes, strings, straps, anything like that. It acts along the line of the rope or string that's exerting it, and it can only ever be a pull. You can't push anything with a rope. An interesting thing about it is that it's really a spring force. When you pull on a rope, it stretches slightly, and you can think of it as being made of all these molecular bonds connecting the atoms. Those stretch a little bit, and they pull back towards the unstretched length of the rope. And that means that a tension can have basically any value. If you pull a little bit on the rope, there's a small tension. If you pull harder, the tension grows, just like with a spring. And we're going to use the capital T to represent tension. The next force we're going to encounter is one that's very common, and unfortunately I find that students have a lot of trouble with it. It's called the normal force, and it's exerted any time a surface is in contact with another surface. So if you think about this ball here, while it's in the middle of its bounce, there's a normal force on it, exerted by this surface that it's hitting. But out here, where it's not in contact with the surface, there's no normal force on it. There's no object that could exert a normal force on it here because it's not touching anything. Now, what we mean by normal is perpendicular. We don't mean ordinary. Remember that another meaning of the word normal is perpendicular. A normal force is always perpendicular to the surface that exerts it. We're going to use a little n to represent normal. And it's also a spring force, just like the tension. When you press on a surface, it bends slightly, and its molecular bonds pull it back towards an unbent shape, and that's what causes the normal force. And I often see students think that normal forces are always up. They're not. They can actually be in any direction. So for example, in the last lecture where you were seeing this book on the table, the normal force that the table exerts on the book is up because the book is sitting on top of the table and the surface of the table is horizontal. And it might not have occurred to you that my hand is pressing down on the book, and that's another normal force, downward, due to my hand. When I was leaning against the wall, the force that the wall was exerting on my hand is a normal force. And then for something sitting on a slope, the normal force ends up being tipped because it still has to be perpendicular to the surface that exerts it. The last force we're going to look at for now is friction, and I have to warn you. Warning, warning, danger, danger. Friction is complicated. So it's exerted by a surface on another surface it's in contact with, just like the normal force. But unlike the normal force, it's always parallel to the surface. So for example, for this car on the slope, the friction force could point uphill. But down the hill is also parallel to the surface. For that matter, there are an infinite number of directions that are parallel to the surface. So we're going to have to talk later about how we decide which way a friction force points, and it's sometimes not easy. There are different kinds of friction. There's kinetic friction, which happens whenever surfaces are slipping against each other. We'll call that Fk. Static friction, which prevents surfaces from slipping against each other. We'll call that Fs. And rolling friction, which happens anytime anything is rolling over something else. Before I close this up, I just want to say that anytime two surfaces are in contact, which is a very common situation, there will be a normal force between them. And then there may be a friction force. And notice how tricky friction is being already. Maybe a friction force. So we've already seen a bit of trickiness with friction. When I was sliding this book across the table, there was a normal force up due to the table. And the table also exerted a kinetic friction on the book. But remember how I was pushing that book. I was pushing down, so there was another normal due to my hand. And I was pushing it using a friction force, which turns out to be a static friction force because my hand wasn't slipping on the book. The last thing I'm going to do in this lecture is just show you how to practice a crucial skill, which is identifying all the forces on an object. So here's a crate, and you're pulling it up a ramp with a rope. We want to know all the forces on the crate. I'm going to draw a circle around the crate. And that circle allows me to say, oh look, the circle crosses the rope, and it crosses the surface. And this has now told us that that's what the crate is in contact with. The crate is in contact with the surface and the rope. And so now we just have to think about what forces could act on it due to those things. Well, the rope, that's an easy one. Ropes exert tensions. The surface, we just looked at that. A surface can exert a normal, and it might exert a friction. And that's it. That's everything the crate is in contact with. And so those are all the contact forces. The only thing remaining is that we have one long-range force to worry about, and that's the weight, gravity. And at that point, we now know we've got all the forces acting on this crate.